We show a novel language model setup for training an unsupervised generative language model with latent syntax. This is a first experiment attempting to model the famously free word order of ancient Greek. We will use a neural CRF parametrization of a graph-based dependency parser as the variational distribution to train an unsupervised recurrent neural network grammar, or RNNG, or URNNG. The challenge of modeling syntactic structure which is explicit in ancient Greek morphology is likely a general problem across all languages. What is explicit in the Greek is that apart from keeping together what belongs together, order serves no function in Greek syntax as it does in other languages. For instance, subject and object cannot be described, let alone defined, in terms of their relative positions. The contribution of syntax to order is precisely that it enables one to talk about the order of subject and object, since these are linearly discrete entities for most of the time. Since being able to learn simple dependencies is presupposed by a predictive model of pragmatic word order, we focus first on syntax as latent dependency grammar. We describe a flexible language model that can naturally be extended with additional prosodic structure. The ancient Greek corpus is strange and fascinating above anything else because of the texts that it contains. It is old and it's actually inseparable from Latin, and the syntax is complex and interesting. As a general example, literature often intentionally exploits semantic ambiguity through ambiguously scoping particles. This also happens in popular phrases like exeis, affexeis, uk en polemo, phnexeis, which is a late translation into Greek of a Latin attribution to an ancient Greek oracle. Here, depending on the scope of the negation particle, in bold, the meaning is either you will go, you will not come because you will die in the war, or you will go, you will come, you will not die in the war. This is of course a fail-safe answer to someone who asks you whether they will return home safe if they leave for war. Don't think too much about it. There is quite the background and recent literature on the type of language modeling that we use, which I will skip over here. Brief information and bibliography are in the presentation file that is attached to this video. And there's also in the last slide, as supplementary material, an example of attraction, which is a kind of complex dependence phenomenon in Greek. Now, leaving the Greek and Latin motivations aside, I will talk about the language modeling, which is of independent interest itself. We characterize a generative language model. This is a joint distribution over sentences and their latent syntactic dependency trees, which are just directed spanning trees associated with each sentence. We obtain the language model P of X by marginalizing the structured latent variable Z in the generative RNNG. X is the observed sequence of words, and Z is an assignment to binary variables that corresponds to the directed arcs in X's projective dependency tree. X0 is just an added root symbol at the beginning of each sequence, and projectivity is defined as a global constraint which prevents dependents from intruding on their ancestors' hierarchy, thus yielding linearly discrete sentence constituents. A variational lower bound on the marginal log likelihood of the language model P of X can be derived by introducing as an inference model, or sentence encoder, a neural CRF dependency parser over the latent variables, namely Q of Z given X. The generative RNNG, or decoder, P of Z and X, and the inference model Q of Z given X are trained simultaneously by optimizing the evidence lower bound with respect to the parameters theta and phi. As a first approximation, we assume an edge-factored model, which means that there is exactly one dependency arc in the latent tree for each word in the observed sentence. A CRF graph-based parser defines the conditional probability of a dependency tree Z given the sentence X through the Gibbs distribution, where the score of a tree is the sum of the scores of all its edges, and the score of a given arc, Sij, represents the strength of the arc's association between words I and J. The neural parametrization of the ARC scores described now is standard in state-of-the-art supervised parsers. However, as far as we know, it has not been used before to train an unsupervised dependency parser. First, we obtain the overall word representations xi by concatenating word and part-of-speech embeddings. Then, we run a bidirectional LSTM over the xi's to obtain the forward and backward hidden states. We then concatenate or just add the appropriate forward and backward hidden states to get the final word embeddings vi. Next, we obtain segment embeddings by dividing a sentence x into three parts, prefix, infix, and suffix, and using LSTM- to obtain segment embeddings. Now, for each dependency arc from xi to xj, we concatenate the embeddings of the head and modifier words I and j, and of the sentence segments, prefix, infix, and suffix. Thus, we get aij, which undergoes a direction-specific linear transformation depending on whether j is to the right or to the left of I, and an element-wise tan h cube activation. And this completes the parametrization of the variational distribution. The generative distribution, the RNNG, models the joint distribution P of x and a of a latent tree Z and an observed sequence X as a sequence of actions AT, where AT may be generate, left reduce, or right reduce. Generate generates a word from the lexicon and adds it to a buffer. Left and right reduce respectively combine the top two words of a stack with a left or right arc and merge them into a single construct. The joint distribution is a product of categoricals for the three actions in the lexicon respectively. It's computed using a softmax on the state embedding UT, which represents the full history. That is, UT represents all actions and generated words up to time t, and it is computed by concatenating a stack embedding ST and a buffer embedding BT. The buffer embedding is just the final hidden state of an LSTM that reads the word embeddings of the generated words in the output buffer. The stack embedding ST, on the other hand, is obtained through a stack LSTM. When a given dependency is predicted, we compose the concatenated embeddings of head and dependent tree fragments, and then feed that composed vector into an LSTM that has rewound its hidden state to the previous element that was extended. The presentation file also contains additional slides on optimizing the evidence lower bound in order to train the encoder and decoder simultaneously, and it also contains a slide on connections with non-projective and with higher order alternatives of the CRF encoder. And finally, there's an abstract sketch of an extension of the generative model to include prosodic structure.